Right. The last quantity we need to talk about for uh, our effort here to quantify motion in one spatial dimension is acceleration. Um, little observation from astronomy. When we think about the motion of our solar system through the Milky Way galaxy, and it's orbiting about two-thirds of the way from galactic center, and an orbit that's a few 100 million years to go around once. Those numbers work out to the Earth moving on the sun at about 100 kilometers per second, roughly. Um, that's pretty fast. You would perhaps be surprised that you're moving that fast through the galaxy. That's a characteristic sort of speed for things that are out in space, outside of the solar system. And despite the fact that you're moving right at this instant at about 100 kilometers per second, chugging along through the Milky Way galaxy, you don't feel that whatsoever. Um, and that is because, as we'll see once we get into Newton's laws of motion, forces, things that you feel and experience, are associated with a change in velocity, not velocity itself. Um, you feel that you're moving 60 miles per hour when you open the window of your car and stick your hand out because your hand is moving through the wind, right? Um, we are not feeling this 100 kilometer per second velocity. We would feel it if that changed. Okay. So the last thing that we need to introduce to quantify motion is acceleration. And it ends at acceleration because ultimately, as we'll see in a little bit, Newton's second law of motion. Newton's second law of motion relates acceleration to forces. And forces, by and large, are not dependent upon any higher order derivatives of position with respect to time. They could be, and there are some sort of off in the corner kinds of examples where we do need higher order derivatives. But certainly for this class and in sort of pedestrian physics, we're quite content to just stop at this derivative of velocity with respect to time. All right, so just as we talked about an average velocity, we can talk about average acceleration. It's not as useful, but we could. So this would be the slope of a chord in a velocity versus time graph. So it's just quite literally, I pick a final time, I pick an initial time, measure the velocity of the final time, measure the velocity of the initial time, and I just take the slope in that plot of velocity versus time. It's the average velocity. What is more useful is to shrink this time interval down to zero and get the slope of the line that's tangent to the curve of velocity versus time, a to a particular time. And that is just acceleration. Now we're not even going to bother to call it instantaneous acceleration. It's acceleration. This is what we mean by acceleration. Acceleration is the first derivative of velocity with respect to time. Since velocity is itself the derivative of position with respect to time, this means that the acceleration is the second time derivative of position with respect to time. To try to help you develop some intuition with this, I want you to play around with one of the original FETs. So this is the moving man. And these were simulations developed at the University of Colorado for um, these basic ideas from Physics 1 and Physics 2. Set it up so that you're going to move the man around from left to right and just have graphs of position versus time and velocity versus time to start with. And then you can go through, once you're familiar with that and play it back and see how it goes, do the same thing with acceleration. I personally find I have trouble moving around my fat hold fingers on my trackpad smoothly enough to have the guide move without a lot of noise once I start taking derivatives. So noise would be like these peaks where I had a didn't seem like a sudden change in position with respect to time, but over a short enough time interval, like the direction of the motion changed. So I get a little kink. To try to do it so it's smooth. So just stayed at a constant position, started moving to the right, stayed at a constant position, more or less, except for this little hiccup, then started moving to the left, so forth. And see the relationship of a positive slope of position versus time is a constant velocity, right? So this straight line corresponds to a constant velocity. And then once you fold an acceleration, whenever there's a constant velocity, the acceleration is zero. I'll see an acceleration when there's a slope in velocity versus time graph. So play around with that, get comfortable with it, and see the relationship between position versus time. The slope of that gives me velocity. Velocity versus time. The slope of that gives me acceleration.